1 minute past 2. Let me get started. So if you can keep your murmurs down and allow me to start. So those who were there last Friday in the class, we were discussing perspective views using, I would say, a 2 station point method. Right? So that's a generic method that allows us to draw a single point perspective, 2 point perspective, and 3 point perspective. Maybe I'll wait. All right, so this is what it is. So if you don't allow me to start now, if you don't permit me to start now, our class is going to get spilled over maybe till about 3:15, 3:30, because I'm going to be introducing a new topic to you. And it looks like I may have to do a little bit of explaining. Okay? So if you allow me to start now, I'll start. I'll have to talk a little about perspective views, and then I'll switch on to space geometry. All right, good, wonderful. So for those who were there last Friday, I had introduced what I call a 2 station point method that allows you to draw perspective of any kind, 1 point, 2 point, 3 point, depending on how you place your object, rather how you place your top view with respect to the picture plane. So if you have your top view, okay, like so, you'll get a single point perspective. If you rotate your top view about an axis that is perpendicular to the screen, you'll get a 2 point perspective. And further, if you rotate your top view in such a way that none of the edges of the top view or none of the edges in the top view are parallel to the picture plane, you'll get a 3 point perspective. The beauty of this method was that you did not have to specify any vanishing point. Okay? So I was working on this example, and we had reached up to this point where I was trying to figure if all the edges of mine, they were converging to 3 different points or not. Okay, and then you guys said, well, the first 2 points, the first 2 vanishing points, they are not lying on the horizon line, and that made me doubt myself. And I immediately went on a defensive and I said, well, I may have made a mistake, and help me try to figure my mistake. And we were searching for answers. And it looks like I have found an answer, and I say that, well, the only mistake that I was making was I was probably not drawing these lines accurately. Okay, so these green lines now are much more accurate, and they allow me to see that these green lines, they tend to vanish at 3 different points. Okay, I'll tell you that they are indeed accurate. Okay. And the top 2 vanishing points, they need not lie on the horizon line. I'll tell you about that. All right, so I'm going to be switching to a new slide, and what you'll notice is that I'll retain these 3 vanishing points, and I'll try to justify that they are indeed the positions that we'll get when we are drawing a 3 point perspective. Okay? Here we go. You see those 3 dots? You do? Yes or no? Come on. Good. Now, this is what I'll do. I'll try to verify these vanishing points. I'm going to go a little fast, so try to follow me. So this is my x-axis of the object, this is my y-axis of the object, the vertical is my z-axis of the object. Okay? This is in the top view. and the corresponding station point where I am standing, the position of the viewer is here, SPT. Now, what I do is I look along the x axis at an object at infinity, okay, that would hit the picture plane. Likewise, I look at an object at infinity along the y direction and the z direction. Okay. These three blue lines, they are going to be hitting the picture plane and they are going to be releasing the respective verticals, right. So, on these verticals, I expect my vanishing points to lie. Fine? With me? With me? Good. I will do the same thing with my profile view. This is what? What axes are these? X and y, and this would be my z axis. I take SPP, the station point in the profile view, I draw a line parallel to the xy axis and hit the picture plane over here, and I draw a line parallel to the z axis and hit my picture plane over here. From here, I am going to be releasing what? The horizontal projections, right. Once I do that, I realize that my vanishing points are essentially the intersection points between the respective vertical projections and the horizontal projections. Okay? Convinced? Convinced? So, I did not make a mistake last time. Okay? Now, I solved another example, and you would see those slides on my web page. So, in this example, I took my picture plane to be passing through vertex A, not vertex E, but vertex A, both in the top view and in the profile view. Okay? Here, what I got was this perspective. The dashed lines are behind, they won't be visible, but they're there for me to verify the vanishing points. I start drawing these lines, they tend to converge to three different locations. Okay? And if I do the same exercise, if I retain these positions of vanishing points, draw my x axis, y axis, z axis in the top view using SPT, draw three lines parallel to the three respective axes, allow them to hit the picture plane here, get the verticals, and then using SPP, the station point in the profile view, draw rays parallel to these three axes here, x, y, and z. Okay, and I release the horizontal projections from there. I tend to see that my vanishing points are, the intersections between the vertical projections and the horizontal projections. Professor Kishore, so you said that you didn't have the proof, but now we have one, so it works. Let me tell you, I have a wonderful team. I'm very fortunate to have a wonderful team of tutors and TAs. And I'm sure you are benefiting a lot in their presence and with the knowledge. So, this is something that I didn't think about, I didn't analyze about. So, Professor Kishore helped me think about this, and it's a wonderful, very elegant way of getting a perspective. The only problem is that you have to figure how to draw the true top and profile views. That's the only problem. That involves two rotations of the object, okay, and once you have that, perspective is straightforward. So, this is what the bottom line was, where we all got stuck Friday. The top two vanishing points need not be on the horizon line or the picture plane. Yeah? Ayush. So, Ayush sent me a link on YouTube teaching me how to draw a circle in perspective. So I'll let him teach you guys. Oh, we can't switch the laptop. I have the. Okay, so we'll probably do that at the end of the class maybe, but perhaps what you can do is you can use this animation and explain how to draw a circle in perspective. Yeah, because that would involve switching time. I have the slides. Yeah. Wait, I have to give you the mic. What do you have this for?
So I don't have this. It's not mine.
Huh?
It's not mine.
Okay.
Okay. So, suppose we have a circle and we have to draw it in perspective view. Then
The right button. Yeah, get the animation first.
so the simple thing is that suppose I have a circle and I have to draw it in the perspective view. What I will take is that I will take the bounding square and first draw it in the perspective view. So this is the bounding square for that circle, which would appear in the perspective view like this. And I will also have these 2 points as these 2 points in the perspective view. Now what I will do is that I will join the 2 diagonals and they will intersect at the point of intersection of these 2 lines.
Yeah. Okay.
Okay, it's not complete, but let me explain it. I will draw the bounding square in the perspective view. Then I will join the 2 diagonals and the 2 lines which are actually these diameters, this diameter and this diameter. This line corresponds to this and this line corresponds to this. So what I have is this is the bounding square. These are the 2 diagonals and these are the 2 other diameters. Then I will join this to this point, this to this point, this to this point, and this to this point. This will form a diamond, and I will then claim that the point of which is this one, this point, this point, this point, and suppose this is the diagonal of this smaller square. Then the midpoint of this point and this point, and same for all the other squares, would lie on the circle. And now I have 8 points and I can join them to form the circle. So this is a much easier way to draw a circle in perspective as compared to making parallel lines and then intersection and then project movement.
So actually speaking, what you have are 2 methods right in front of you to draw a perspective to draw a circle in perspective. Okay, method 1 is what you see on screen, right? So you have the bounding circle enclosing bounding box enclosing a circle. Okay, you have 8 points on the circle. Okay, so corresponding to this bounding box, you draw this box in perspective. You locate these points corresponding to these gray points here. Okay. The first method, you draw these 2 diagonals, okay, and then locate these red dots on those diagonals. Okay. Now, corresponding diagonals in perspective would be these 2 diagonals joining the opposite vertices. Okay. Now, you would know that this would be in true length. You take this distance from here to here. You take this distance from here to here, measure these 2 distances here, okay. Project a ray starting from here up to the vanishing point, and then another one starting from here up to the vanishing point. These 2 rays are going to be intersecting the two diagonals at 4 red points. That's method number 1. Method number 2 is what Ayush proposed. Instead of doing that, instead of having these, okay, join these 4 points, you'll be making a diamond, okay, and then you would have this square, this square, this square, this square. You'll have a diamond here, 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 and here, and then what would you do, Ayush? You would have a midpoint. You would have the midpoint of this. So you'd have a midpoint of this, midpoint of this, midpoint of this, midpoint of this. You'll get these 4 points and then draw another circle. Yeah?
The second method is not exact.
Yeah. So the second method, of course, is probably not exact, but it is relatively faster than this method. This method happens to be a little more precise. Yeah? Okay. So straighten your back. If you have seat belts, buckle yourself and get ready to sleep. A new topic, space geometry. One request that I would want to make is, I'll try to explain this as best as I can, but just in case if I'm not clear enough, do raise your hand, and if I cannot see your hand, do get up. If I still can't see you, use the chair. Stand up on the chair, raise both hands and say, "Sir, stop. I didn't understand," and I'll be happy to explain that to you. Okay, so I want your attention, I want your eyes, and I want your ears over here. Okay? And I want you to prompt me if you are with me every time. Okay? Things will be a little confusing. All right, I'll start with the orthographic projections. This is the XZ plane. Okay? This is the XY plane. Almost all discussion will be with the third angle projection scheme in mind. Okay? Although it's not important. Okay? So which view is this? Which view would this give you? Front view. Which view would this give you? Top view. Wonderful. The front view, the top view. The front view will be on a vertical plane, so I would call the bottom plane as the vertical plane. The top view will be on the horizontal plane, and I'll call that as the horizontal plane. Okay, so there will be a switch in notations, in terminology that you need to understand. Okay, so this is the front view, or what plane? Top view and what plane? Good. Imagine that I have a line whose projection in the top view is a horizontal line, and the same line in 3 dimensions whose projection in the front view or vertical plane is an inclined line. Okay? A little bit about coordinate geometry, very simple. Let's say this is x1, z1. Let's say this is x2, z2. The coordinates of this vertex, x1, z1. Coordinates of this vertex, x2, z2. Okay? In the horizontal plane, let's say the coordinates are x1, y1 and x2, y2. Okay? All right. What would be the length, rather the true length of this line whose projections are given there? Huh? This? Delta x the whole squared plus delta y the whole squared plus delta z the whole squared, square root of that. Okay? Now, since the projection of this line in the top view is horizontal, y1 is equal to y2. Okay? And if I set this to 0, my true length will be delta x the whole squared plus delta y the whole squared, right? Sorry, delta z the whole squared, delta z the whole squared. Okay? With me? All right. Okay? Now, do you see the projection of a line where you can find this length? Do you see the projection of the line where you can find this length? On screen. Yes? Which one is it? The front view. This one here. x1 minus x2 the whole squared plus z1 minus z2 the whole squared. This is in true length. All right? So, if this is not clear, I have this pointer here. It is oriented in some way in space. Okay? What you see is the front view of this. What you see is the front view of this. Okay? In the top view, I would see a horizontal projection of this line. Okay? This is what these two projections are. With me? With me? Good. So, this is just for your understanding. In your laboratory exercises, you will not be needing coordinate geometry. You will essentially be working with geometry. Okay? So, this is in true length, and I label this length as TL, true length. Another scenario, xz plane, the front plane or the vertical plane, and xy plane, the top view or horizontal plane. This time in the horizontal plane, I have a line or the projection of a line inclined differently. It is not horizontal. And in the front view, that projection is horizontal. Coordinates x1 z1, x2 z2, x1 y1, and x2 y2. The x's remain the same. Okay, the z's and the y's, they get changed. Now, what do you expect the true length of a line to be in this case? In the frontal view, on the vertical plane, z1 is z2. Look at that equation of yours from coordinate geometry. z1 minus z2 the whole square is 0. Okay, so your true length is delta x the whole squared plus delta y the whole squared, which actually you can get from here. So, this is TL. Okay. Now, these two examples should tell you something. These two examples should tell you something. If I have the projection of a line which is horizontal either in the front plane, in the vertical plane, front view, or it is horizontal in the horizontal plane or the top view, I would be getting the true length of that line in the other view. Do I make sense? Do I make sense? Good. Now, imagine this line in space. Okay, and this line is oriented in such a way that you get the projection which is not horizontal in the front plane, in the front view, vertical plane, and it is not horizontal also in the top view, the horizontal plane. What do you do in that case? How do you find the true length? How do you find the true length? You can use the experience from the two previous examples. Yeah? You can make one of the projections horizontal. If you do that, the other projection will give you the true length of that line. Nah? Yes or no? Okay. So, what we have is the method of rotation for that. Let us say you rotate the projection in the horizontal plane or the top view by some angle. Okay? That rotation is about what axis? The z axis. This axis over here. So when you are rotating that, what's going to happen to the line? What's going to happen to that black line? It gets rotated, nah? Okay, and you're going to make this projection horizontal so that you can get the true length of a line over here, right? Now what happens after that? What happens to the corresponding projection of the line here? Any idea? Okay, let me get back. Let's say you're rotating the line about this point. Okay? You're rotating the line about this point. Okay? About the z axis. So this point remains fixed. Okay? Let's go up. What happens to the x, comma y, comma z coordinates of this point? Would the x coordinate change? Would the y coordinate change? Would the z coordinate change? The z coordinate will not change. Come back to this view. Okay? The z coordinate of this point would not change. So you can expect the z coordinate to be lying somewhere on the horizontal, green line. True? True? Okay. And you already have the position of this point in the top view. Use this projection, get this point. Okay. So if you have rotated the line so that this projection happens to be horizontal, okay, this would give you what? The length of the red line will be the same. Nah? The length, so if you are rotating this line, the length doesn't change. Yeah? So this green line here would represent what? The true length of this line in 3 dimensions. Do you agree? Do you agree? Okay. Who doesn't? Yeah?
We are rotating the line along Z. How is it going to rotate about Y?
So remember that these two black lines, these are projections, number 1. Okay? So if you are rotating the line about the z axis, its projection will also get rotated. What's your question? Yeah, in the top view. It is not getting rotated about the y axis. Perhaps let me come back to the other example. Let me come to the other example that would help you understand this better. Okay? This is okay, right? Is this okay? The same example. Okay? Now let's say you have this line. Okay? Now you see the projection of this line in the front view. Okay? Now I'm going to rotate this projection in such a way that it becomes horizontal. Okay? I'm going to rotate this in such a way that this becomes horizontal. Okay? This rotation is about what axis? The y axis. Okay? Now of course this length would not change. This length, what you see, would not change. Right? Okay. What would happen to the y coordinate here? No change. I'm rotating the line about this point, so this point remains fixed in space. The y coordinate of this line doesn't change. Okay, I already have this point located over here. I take its projection. This would give me the true length of a line. Now what do I essentially mean by true length? let's say I have this line, and what you see is this line in this plane. Yeah? Now, if I rotate this line so that this line becomes parallel to the plane of sight, it's only then that you're going to be getting the true length of this line, not otherwise. Right? Right? Once again, if I make this line parallel to the plane, to the vertical plane, it's only then you are going to be getting the true length of that line. Yeah? What's that? I can't hear you. Yeah? We are using both planes for our view. In that example, the line becomes parallel to the horizontal plane. That's the reason why you get the true length of that line in the horizontal plane. In the previous example, the line becomes parallel to the front plane. That's the reason why you get the line in true length in the front plane. Okay? You know, you guys are tired, I guess, from the Galaxy thing, so I would suggest that you take out your notebooks and pens and start scribbling, because this is not very difficult. So with that, you'll also follow what I say a lot better, and then it'll keep you active, and then it'll keep me active. Okay? So is this method of rotation clear to you all? Is this clear? Should I go back and go through these two examples again? Yes sir, no sir? Everybody with me? Nah. I'll go back. All right, so have your sketch pads on in front of you, have your pencils or pens in front of you. Draw the projections of a three-dimensional line in front and top view, like what you see. Done? Done? Okay. Now the trick is very simple. You want to see one of the projections either in the front view or the top view to be horizontal. If you see that, the other projection will ensure that your three-dimensional line is parallel to the plane, okay, and therefore you'll be getting the true length of the line. Fine? All right. In this example, rotate the top projection so that it becomes horizontal. Okay, when you see that, you're rotating this line about the z-axis, so the z coordinate of this point doesn't change. You're rotating the entire line about this point, so this point remains fixed in space. If the z-axis here doesn't change, if the z coordinate doesn't change, then this point has to lie on the horizontal. If it lies on the horizontal, you already have this point located in the top, drop a projection, you get the new point, and therefore you get your line parallel to this vertical plane, and therefore in true length. Fine? Okay? All right. Let's do the same thing but reverse. The same example. Now what I would want to do is I would want to see this projection to be horizontal. Okay? So I would rotate this projection about this point and about the y-axis. Okay, the length of this projection doesn't change. Now if I am rotating this line about the y axis, the y coordinate of this point doesn't change. So this point has to lie on this horizontal, fine. And then I already have this point located over here. I take the projection up, I locate that point. This line now becomes parallel to the horizontal plane. Okay? Straightforward? All right. This is going to be very boring or could be interesting depending on how you take it. So given these two projections of a line oriented arbitrarily in three-dimensional space, let me try to locate the actual line in space. So I have this box. Okay? Stay with me, stay with me. This is my what? What is this? Front view or vertical plane. That is my top view or the horizontal plane. Okay? Let me get this blue line. Let me work with the horizontal plane first and mark it over here. The little blue line, mark it over there. This length is the same as this length. Okay? So this blue line over there represents this guy. With me? With me? All right. Let's do the same exercise with the vertical plane. The green line, mark it there. Second green line, mark it there. And this green line is actually this guy here. Okay? You got a three-dimensional box, you got two projections. Is it possible for you to look at the actual line? Okay. Possibly like this. Like this. Do you all agree that this is the actual line? All right. Good. So let's say my method of rotation is boring. It's not good enough. Okay? How do I get the true length of this line? How do I get the true length of this line? The only way I can get the true length of this line is to make sure that I'm visualizing that line, okay, from a plane which is parallel to the line. Okay? Not otherwise. The plane has to be parallel to this line. Fine? So I have to figure out that plane first. Of course, that black line will be in true length. Fine? Now imagine that I have a plane that contains the blue line on top, the blue projection. Imagine that I have this plane here that contains that blue projection. Okay? Now my question is very simple. Would the actual three-dimensional line, which is the black line within that box, would that line be parallel to this plane? Or no? Rather, let me rephrase, would that black line actually lie on that plane? Do you all agree? So if I view that line from that plane, dotted plane, will I be getting the true length of the line? Yeah? Okay. Good. Do you all agree? It doesn't really matter where I locate that plane in space, so long as that plane is parallel to itself. So instead of using that dotted plane, perhaps I can shift that plane forward or backward, so long as I ensure that the plane is parallel. Fine? All right. Now what I do is I drop verticals from the corresponding projections onto that plane. Okay? So these red verticals from this projection which is over here, onto the plane. Okay, and I can shift that black line to actually lie on this plane. Right? Fine? All right. Now I want you guys to be attentive here. I want you guys to follow this carefully. This is a hinge line that separates what from what? The horizontal plane from the vertical plane. Good. What I would want to do is, once I have located this plane in some way, okay, and this plane is inclined to both the vertical plane and the horizontal plane, okay, what I would want to do is, I would imagine that there is a plane here and there is a hinge line between, say, the horizontal plane and this plane. And just as what I do in case of orthographic views, I flip this, what I call the auxiliary plane, up. So this red plane is the auxiliary plane here. Okay? So this is what I do. Okay? And if I flip it up, and if I have that red line contained on that plane, this one, I would be able to get the true length. Okay? All right? Let me go back and explain this again. This is for your own good. So this example here, I got the projections of a three-dimensional line on the vertical plane, on the horizontal plane. Okay? I try to locate the actual three-dimensional line within a three-dimensional box. So what I do is, I first draw the projection, or I first draw that projection on the horizontal plane. I draw the corresponding projection on the vertical plane, and then I extend those projections and I get the actual three-dimensional line. And then what my proposal is, or what my proposition is, that if I draw a plane which passes through that blue line on top, I would be able to capture the actual three-dimensional line, which is the black line, within that plane. And that black line, of course, is true line, therefore it would be having the true length. So I would be able to capture, so if I draw a plane that passes through this blue projection, which is this one here, I capture this black line, the actual three-dimensional object, on that plane, and it doesn't really matter if the plane is there or if it's shifted by some amount. I can always shift my black line and ensure that it still lies on that plane. Okay? And all I need to do is process what I call this new plane as the auxiliary plane in such a way that I can see the true length of the line. Okay? So the first thing I would do is, I would identify two hinge lines. You already know one of them. The purple one is the new one. Now this is quite tedious. This is quite tedious. I would want to work with this figure over here. And I want your attention. So this figure, I have it on the left for reference. Follow the color codes. The brown hinge line is this one. Do you agree? Okay. Now notice that this purple hinge line is parallel to the projection of that three-dimensional line in the top view. Notice that. Do you agree? Good. Now of course, the projections are going to be perpendicular to the hinge lines, wherever they are, right? So I draw projections from this projection of the line perpendicular to this purple hinge line. Fine? All with me so far? All right. Now look at this line here. Look at this distance here. This distance is of this point, okay, from this brown hinge line. Okay, so this distance here. Okay. What I would do is I would take the same distance, measure from this point of the hinge line and get this point. Okay. Look at that small distance. I would stay on this projection line and take the same distance from here to here. Okay. And I'll join these guys. And then I'll say that this is the true length of my three-dimensional line. Do you agree? Do you agree? Or you're lost? Lost? Good. Back again. So far so good here? So far so good here? So you see I have two hinge lines, one is the brown hinge line and the other one is the purple hinge line. The brown hinge line is relating the front view and the top view. The purple hinge line is relating the horizontal plane here and the red plane, the auxiliary plane. Okay? So I draw this purple line here. So go back to your understanding about orthographic views. So what you do here? So you have your front view here, your top view here. Okay? You just flip this guy over, don't you? Don't you? Yeah? Now imagine that you have your top view here and you have your auxiliary plane at some inclination to this, like this. Yeah? We are doing essentially the same thing. We are flipping this guy over. In relation to the horizontal plane, we are flipping this guy over. We are doing exactly the same thing. Yeah? Now, look at these green lines and look at these green lines. These green lines, they measure the distance of this point from this brown hinge line and they measure the distance of this point from this brown hinge line. So far so good? So far so good? So these are my corresponding green lines. Fine? Fine? Now go back to your three-dimensional box here and try to identify and try to verify if this distance is the same as this distance from the purple hinge line. Is it? Is it? Likewise, for this, try to verify if this distance is the same as this distance from the purple hinge line. It is? It is or not? Which is what I do here. Okay? So what I've done is I have drawn an auxiliary plane and I have related that auxiliary plane to the horizontal plane. So I have this purple hinge line here. Okay, and I have taken this distance and this distance and measured this and this to be the same. And of course, the projections have to be perpendicular to the hinge lines. So these gray projections are perpendicular to the purple hinge line. Okay, and if I flip that auxiliary plane over, that auxiliary plane is going to be containing the true three-dimensional line. And it's going to be therefore in true length. You agree? So a little bit of practice and you'll be okay. You know, I can only imagine how you are trained in coaching classes. Okay? So this is that version of it. The instructor, pardon me if I'm wrong, but the instructor in one of your coaching classes will say, well, you know what, forget about this. It's too tedious. You don't understand that. You don't want to waste time understanding that. This is a quicker version. You have these two views, all right? You have this hinge line? Yes or no?
Yes, sir.
Good. Step number 1. Is that true? Okay. No. Whatever, I'm just enacting. Draw a hinge line which is parallel to the projection in the top view. Step number 1. So you have this hinge line. It could be here, it could be here, it doesn't matter. Fine? Step number 2. Make projections perpendicular to this hinge line from both these points. Step number 3. Measure this distance and mark a point on this projection with the same distance as this. Number 4. Measure this distance, mark this point over here on this projection line with the same distance. Step number 5. Yeah, step number 5. Yeah, you can go. No, stay back. No, stay back, man. Yeah.
What is the benefit of drawing that purple line? You would have directly drawn the line from there.
Okay, so somebody here asked me what is the benefit of drawing that purple line if you can draw the projections directly from that black line. And I'll tell you what the benefit is. So if you don't draw this line, and if you take projections directly from here, this is a very simple example. But in more complex examples, you're going to be needing this view not once, not twice, but quite a few times. When you need this view, you don't want to lose this projection. If you lose that, you're confused. Right? Two more minutes and I'll let you go. Sleep and get ready for Galaxy in the evening. I can follow the same 5 steps. With reference to the vertical plane. Not from the horizontal plane, but with reference to the vertical plane. This is how. Well, I've already done that. Yeah, fine. Maybe I'll, yeah. It doesn't really matter where you position this purple line. You can position it anywhere, you'll still be getting the same true length of a line. So this is one quick example. So the purple line is closer now to the projection in the horizontal plane. The same exercise, 5 steps, okay, you can get the true length, okay, and if you compare with the line in true length from the previous example, this was this. So in fact, these lines are going to be parallel. Okay, I can do the same thing in reference to the vertical plane or the front view, okay, nothing changes. Step 1. Step 1? No, yes sir. Step 1, what is step 1? Draw a hinge line parallel to the projection in the vertical plane. Step 2, draw projection lines. Stay with me. Step number 3, measure that distance and mark that distance over here. Step number 4, measure this distance and you're going to be measuring these distances from the hinge line. Mark that distance over here. You got 2 points, join these 2 points, you get a line which is going to be parallel to the auxiliary plane, and therefore it's going to be in true length. So this is a 3-dimensional line which is parallel to the auxiliary plane and therefore in true length.